here it comes out at like about 4 minutes, here about 8. And that time is like a measure for the capacity. And you also want an as high capacity as possible. So the ZK5 form has a higher capacity, a higher working capacity, and also there are no diffusional limitations, because what you see is these profiles, what you call breakthrough profiles, they are always very straight. They are never broad like here. And I want a straight profile. So ZK5 is better. That's one take-home message. The other one here, it's more a scientific message, is for the low silica potassium form. You see that I have very broad profiles. So it means strong diffusional limitations. And the reason for that is that there are a lot of cations here in these 8-membered ring windows. And they block both molecules. That's something you don't want. Now, let's look further. So, I did a performance comparison based on working capacities, selectivities, and LUB, which means it's a measure for diffusion limitations. And from this graph, the outside is always the top one. So if you're near the outskirts, you're the best one. And from the chart, believe me, the best KF5 form is lithium ZK5. And that's because the CO2 strongly interacts with the lithium. It's an equilibrium effect. However, if you look at the graph, you see that this material, 13X, which is like the industry standard, is still better. And that's also shown by the pressure swing simulations. So I cannot beat industrial standard with equilibrium effects. And therefore, I ask myself the question, can I do it with a kinetic effect? So the kinetic limitations is because there are strong cations, there are large cations, in these 8-membered ring windows. And a lot of them. So maybe I can use a structure with a bit less cations. And those structures are what we call rubidium and cesium ZK5. And then I checked, can I use the kinetic effect to separate the CO2 from the methane? Well, the answer is yes. It works. These rubidium and cesium compounds, they separate the CO2 from the methane by blocking the methane and leaving the CO2 through, which you can see in the graph. I have very low mass transfer coefficients for methane, but the problem is the methane still goes in, and therefore it's still not beating the industrial standard. So here 13X is still the winner, and we need another material to beat the industrial standard probably. Final comment I want to make is about the trapdoor effect. I already talked about equilibrium effect, kinetic effect. Is there also an impact of the trapdoor effect on this zeolite? Well, the trapdoor effect is that one molecule is strong enough to push away this cation and go in. CO2 can do this, for example. This has been shown by one of my colleagues in Australia, Dr. Chang. He discovered this mechanism. And the question then, how can I see whether a zeolite is a trapdoor zeolite? If a zeolite is a trapdoor zeolite, there's no adsorption of argon at very low temperature. There are strong diffusion limitations for methane, but CO2 still goes in, and there's a spontaneous migration of cations which leads to a maximum in the adsorption of methane or nitrogen as a function of temperature. Now, is one of my zeolites a trapdoor zeolite? I first checked it for the rubidium and the cesium ZK5 zeolites. And for them, you see no argon adsorption at low temperatures, strong diffusion limitation for methane, and still CO2 adsorption. So the question is there a maximum in the adsorbed amount as a function of the temperature? Well, answer is no. Down to 261 Kelvin, there is no, it's minus 30 degrees about, sorry, minus 10, minus 12. There is no maximum. Whereas for a molecular trapdoor zeolite, you see, there's a maximum. And here, there's no maximum. So on these zeolites, there's no trapdoor effect. And And maybe on the low silica potassium form, there could be a trapdoor effect. Because on this zeolite, there's no argon adsorption, still diffusion limitations for methane, but CO2 is being absorbed. And yeah, so is there then a maximum? Well, the answer is I don't know yet. But this zeolite is filled with cations. So probably the effect is there. To summarize all the measurements, I use this slide. Here you see the impact of the different separation mechanisms. So on the lithium compounds, equilibrium effect is dominant. On the rubidium and the cesium compounds, you have strong kinetic effects. And on the low silica form, you have strong kinetic effects and a large potential impact of the trapdoor effect. So to conclude my talk, I want to say that there are out there unexplored adsorption separation mechanisms which offer tremendous potential in diverse industrially relevant separations. And that I've been showing in the 3 parts. So in the first part about the chain length dependent adsorption, I showed you that the SAPO34 is able to separate short chain molecules from longer chain molecules with a selective retention of the short chain molecule. And that's relevant for the biobutanol product. In the second part, I've shown you that by implementing loading dependent adsorption parameters, combining to the flow model, that I can finally get and capture the trends in capacities, selectivities, and breakthrough profiles. And that was relevant for separation of C8 alkyl aromatics. And finally, in part 3, I investigate the impact of the equilibrium, kinetic, and the trapdoor effect on the KFI zeolite. And that in the context of CO2 methane separation, which is relevant for biogas separation and natural gas purification. So, thank you very much for your attention, and if you have any questions, don't be scared to ask them.
Thank you, Tom, for this interesting and clear presentation. The jury already had a chance to go into scientific discussion with Tom concerning his work, but I'm pretty sure that there are still some questions remaining, so I will start with the one coming from far away. Professor Gandani, do you still have questions?
So Tom, you've covered a lot of subjects, and you gave a very nice overview tonight. Of these subjects, these separations, which ones do you think that you still want to investigate further and why?
Economically, or
I think you're right.
Economically, I think the biobutanol separation is most important because you only have an adsorbent to separate the different alcohols, and within our group we're already looking at other adsorbents which I showed you in the process, adsorbent 1 and adsorbent 2. On these adsorbents we still need to look at. We have, yeah, it's published, so I can say that there are like good metal organic frameworks to separate the alcohols from the water. The main thing which needs to be looked at there is like the desorption. Within the context of part 2, I would say there the zeolites are much better than the most we have been investigating. So most of the work is done there in my opinion. And in part 3, it's still scientifically highly relevant to check whether this molecular trapdoor effect is really there on the potassium form or on any other zeolite which might show this effect, I think. And still, yeah, we can, yeah, there are materials out there which are better than 30 for biogas separation.
So as a follow-on, the trapdoor effect.
Yeah.
Basically, whenever you're trying to do a kinetic separation.
Whenever
you're trying to do a kinetic separation and control the, what are the practical limitations of that when you scale up the process?
The thing is, you have to ensure that in the end you don't force the methane inside, because otherwise yeah, your recovery and purity will go down. And that's why often with a molecular trap or zeolite, we need to go to lower flow rates to ensure that the methane doesn't go in. And to make sure, and as a result, you have a lower throughput. Yeah, you don't have, it's impossible to go to very high pressure, otherwise in the end, the methane is forced in, that's what we don't know.
Professor Martens?
Yeah, thank you. Mr. Chairman, Tom, I really enjoyed your presentation. I must say you are an ambassador for the absorption community, so please go on like this and advertise absorption and all what you can do with it. You were expecting probably a question about hardware, but I will ask a totally different question. Sometimes, well, you did investigations of many different types of absorption, alcohols, gases, liquids, aromatics, on different types of materials, zeolites, MOFs. So you must have a good feeling of why sometimes models and real behavior are somewhat deviating. And there are three possible explanations. Either the materials aren't perfect, and we all know you have nice models there, but the real world is that many of these materials contain lots of defects. And it's known in MOFs, for instance, that often there is a missing linkage, or in zeolite there is a broken bond, an hydroxyl group instead of a cation, an acid site, etc. So that can be one part of the explanation why the model and the real world behavior is not right. It could also be that the experiments you do are experimental errors and there are deviations. Or the model can be a bit too rough. So what is your feeling now after a couple of years of work? The materials, the models, or the experiments, where is the, well, to get things more perfect and cleaner, what would be, or is it a contribution of all the effects that makes sometimes the images a bit...
You're more like referring to the MOF problem.
No, general question.
Because in the MOF it's easiest to answer the question, because with the MOFs you start with pure component adsorption. That's what we measure. Then we do like a dynamic experiment which we want to model. First thing is you measure isothermal power. But in reality you use a pellet. So there's already a binding molecule to keep them together, which has an effect on your adsorption during the dynamic experiment. Second, it's a mixture. So, and your isotherm in the mixture condition is different from the isotherm in the pure component situation. And then finally, within the models I use, we make a quite rough approximation, which we have been discussing. No. Okay, this one. So here, we make a model to say that the orthoxylene goes into the open pore form. But we say, for the ethylbenzene, we actually say that the isotherm goes like this. But in reality, yeah, there's a little step in there. And we just say, no, it's not there. Just a first rough approximation. So there's like a contribution from, in the model, from the material, the pelletization, the binder. It's not a perfect model. It's still, it's always the case for the model. And then the model is not that wrong, I would say. There's a really nice approximation, I would say.
And your experiments are perfect.
Let's say the experiments are designed as accurate as possible.
Thank you very much.
Mr. Goldrum?
Yeah, I want to come back on the first question, but in a different approach. No, on the trapdoor, and you explored very subtle effects that produce separations in these for CO2 methane. But I was wondering, if you look at the trapdoor or kinetic separation, you say, yeah, it doesn't work very well because the second molecule goes in a little bit.
Yeah.
But isn't that the case always with the kinetic separation? Unless you have really a steric separation where the second molecule doesn't go in. And nevertheless, nitrogen, oxygen are very well separated on a carbon molecular sieve. And you get better performance than what they are getting. So aren't you a bit pessimistic there? Or is there another reason why this kinetic separation you would not like to do it?
It works really well. But the problem is, there's a material out there,
13x.
13x, which is better. So yeah, who wants to buy a material which is less good? So
Okay.
I mean,
agree with that. But then talking about 13x, you checked PSA in all your work, and it's logical because you were in a group in Australia that does essentially PSA. But is that the best method to exploit these materials? Wouldn't you do TSA or use the material in a membrane or whatever?
I believe for the PSA separation, 13x is not the best material. There's a better material out there which is USY, because it has a less steep isotherm than the CO2, so it's easier to get the CO2 out. Now, the question whether we should use for this separation, for CO2 methane in biogas separation, I believe PSA is better than TSA. But if we look at CO2 nitrogen separation, then probably TSA, I mean, we still need to explore a lot of TSA before we can say that PSA is better or worse than TSA, thermal string adsorption. For example, people are now, for example, the group of Paul Webby where I was, they are looking at to use chemical solvents with TSA. And it's, yeah, the first results seem to be very interesting, but there's still like 5 years of research needed before we can really say this one is better than the other one.
Thank you.
Professor Pinto?
Thank you very much, Mr. Chairman. I really enjoyed listening to your presentation as an electrical engineer. You gave me the impression that I understood everything, which is very nice. So you mentioned in the beginning that clean air is important. I fully agree. You also showed that zeolites can be used to capture carbon dioxide.
Yes.
So is it feasible to use zeolites in chimneys of industrial plants to capture CO2? And if yes, what about the storage about the CO2?
I mean, it's completely possible. It depends how much money you want to give me to put it there. Because the idea is, if we put it there, an adsorption unit to capture the CO2 from the power plant or from any industrial process, it will cost, nowadays it will cost between $40 and $100 per ton CO2 capture. To capture it and put it into the ground. However, with a few years of research, maybe we can bring it down to 30 to 40, maybe 20. And the incentive to do this is only there if you give a tax to people for every ton of carbon they put into the air. As long as you don't tax them for the carbon which they put into the air, there's no incentive to recover the CO2 from the chimney. So if you don't let them pay for the CO2 they emit, then they just don't care.
So you would advise policymakers to raise taxes?
Actually, it's the only way to. The technology is there. It's just a matter of putting it. Everything is proven. Everything works. You just have to come with a cold hard car and put it there. It's not a question of science. It's a question of policy, in my opinion. And for the storage, let's say there are two big projects like Sligo in Norwegia and Inshallah in Algeria. where they have been putting like already for 10 years like 1 million ton of CO2 into the ground for every year. So there's like 10 times 1, 10 million ton of CO2 into the underground rock formations, and the CO2 doesn't seem to go out. So, I mean, I'm not going to say that it's unsafe. I'm going to say I fear that if you want to stay in a scenario where we keep the amount of carbon, CO2 particles about below 450 ppm in 2020 or 2050, in the end there must be CCS. And it will contribute like to 10 to 20% of the reduction in CO2 emission, and the rest has to come from renewable energy, energy efficiency, better isolation of houses, and so on. It's like an and solution. It's not the solution, CCS, but it's part of the solution, whether you like it or not.
Thank you very much. It's very clear that you are really excited about this.
Thank you. Does the promoter still has questions?
No, thank you, Chairman. Tom and I really have to say that had so many interesting discussions over the past 4 years that I don't want to spoil it today.
Okay. Are there any questions in the podium? Yes?
I have a question about the 13x. So I followed your presentation for a large part up to the point where you started talking about 13x. You got me really curious as to what 13x actually is. Because you said a lot of this area of absorption is unexplored, but there is an industry standard, it's a material, it works very well. So obviously there must have been a lot of research on this. Is it not a zeolite maybe?
It's a zeolite.
It is.
It's actually, this structure is actually 13x. It's a phosphite, what we call it. The type of zeolite is called phosphite, and this is 13x. And there are the marbles which are in the 13x, the cations, it's sodium. It's sodium X actually. 13x is the same as sodium X. And it's a phosphite, and the nice thing about this phosphite is that it has a very low silicium to aluminum ratio. So there are a lot of marbles. And the thing is that your window here, it's not an 8-membered ring window like the zeolites I investigated. It's a 12-membered ring window. So even if there's a cation here, there's still enough space for the CO2 to go in without diffusion limitations. And therefore, this is really a great material for CO2 absorption. It's very hard to beat it. The only problem is that since the isotherm is very steep, the thing is that you need to go to very low pressure to remove the CO2. So you need to go to vacuum, and vacuum, that's a lot of money.
And this is what you were trying to improve.
And
this is what you were trying to improve.
Yeah. Okay. We need to try to find a zeolite which is better. And one idea is to use the same structure but a slightly lower amount of cations, such that the isotherm is less steep, and I need to go to lower pressures to remove the CO2. And then I'm better. That's what they want to do with biogas in India, for example. It's a project we were investigating when I was in Norway.
Any more questions in the audience? No?
Okay, cool. In terms of CO2 methane separation,
Yeah.
a lot of the separation also happens straight from natural gas, but CO2 is present in the wells.
Yeah.
And then the standard technologies
It's
are
absorption.
chemical solvents or physical solvents or membranes, which often require either big compressors or very high reboiler fluids and so on. How far do you think this absorption technology is still away from beating these technologies and becoming, let's say, more competitive, or being able to beat these out of the market?
I think it's already there. Isn't there a company, Molecular Gates, but it's been bought by another company? You should know it. And they work with titanosilicate, and there it's a kinetic separation. It means that the CO2 goes through the material and the methane goes in, and as such you separate them. So the materials to beat the standard chemical absorption are already there. The big problem is that when your gas comes out of the earth, it's at extremely high pressure, like 50 to 100 bars, somewhere like between those values. And at those pressures, the pressure is so high that in the end, you also get a lot of methane inside your pores. So maybe for natural gas separation, the zeolite is maybe not the best type of material. It's much better for the biogas. For the higher pressures, if you could find a selective MOF, if I'm right, people at Sintef are already looking at it. So you can use like UO66 MOFs to do this, because they have a really high capacity and selectivity at high pressures, which zeolites have that, don't have. They have the high selectivity and high capacity at low pressures.
Any more questions? Yes?
Do you see any medical application of your experimentation?
Medical.
Because I see it's much more interesting for this sector.
Well, it's already there. The separation of nitrogen from oxygen. It's done with. I don't have the structure here with me. It's another type of structure. It's called LTA structure. It's zeolite 4A. I showed you how it works. In the end, the nitrogen goes in and the oxygen doesn't. So a lot of the oxygen tanks you see in your hospitals, it's made by adsorption. It's produced with adsorption. So it's already there. And also, whenever you need dry air without water inside, we use a kinetic separation. It's like the water goes inside, the water stays inside, and all the rest doesn't. So, and yeah, that are the main applications. You can use zeolites for, it has like a huge amount of technology. When it's used for detergent, catalysis, cat litter, for example. It absorbs radioactive waste. Like in the sea around Fukushima, there are tons of zeolites just to absorb all the radioactive waste. So it's a very interesting material.
More questions? If not, then the jury will leave the room, but don't run away. We will come back to let you know if Tom will get his degree or not.
Separate the butanol from the other alcohols such as acetone, ethanol, and so on. And that's where my adsorbent SAPO34 comes in. And initially, I measured then adsorbed amount as a function of the concentration, which is shown, first exploration, of course. That's me watching sky in northern Australia. So, this is what I was talking about. These are the isotherms as a function of the liquid concentration. And what you can really see, if you would plot it again, but then because on the left it's in a mass per mass zeolite, and now on the right I plot it as the number of molecules in the pores. You clearly see there are like two cutoffs, one between ethanol and propanol, and one between butanol and the higher alcohols. What is the reason for that? For these cutoffs, these changes in capacity? Well, we need to study them. Well, what we do here is to compare the length of the alcohols with the dimensions of the cage. And this is the cage of the adsorbent. So we have a width of 6.7 and a length of 10. And before the first cutoff, I have methanol and ethanol. And they are in my pore along the perpendicular axis, like this. And between the first and the second cutoff, I have propanol and butanol, and they are in the pores not along